I'm Damien de Mijolla. I'm from University College London, and I'm going to be talking about what Diane said. This is joint work with Melissa Ness from Columbia University, and it's not yet been published, but it should be on the archive soon in the coming month, hopefully. So before I begin talking about the method, I kind of want to talk about the current way we extract stellar parameters from stars. And so when we have large-scale surveys like APOGEE or GALA, we have very large numbers of spectra, but we're not interested in the spectra per se usually. Rather, we're interested in the stellar labels we can derive from them. And to get these stellar labels, a kind of more established way of doing this is to use computer simulations to describe essentially the ground truth of what a star-stellar spectrum should look like. But the problem is it's quite difficult to create these synthetic spectra to be entirely faithful to observations. We need to make some assumptions to generate them, such as local thermodynamic equilibrium, and so we also ignore instrumental systematics. And all of this negatively impacts the precision of our stellar labels and acts as a bottleneck in our ability to estimate them. So ideally, we'd like to do away with these synthetic spectra if at all possible. And this is what I'm talking about, is a method for doing this. Now, the idea of our approach is instead of using synthetic spectra, we want to exploit the chemical homogeneity of open clusters to find other chemically similar stars. And to do this, we have to make a few assumptions. We need to assume that the open clusters are chemically homogeneous, but we also need to assume that they can only be identified from spectra by the chemistry. And what it means when we make these assumptions is that chemically homogeneous stars and open cluster stellar siblings are the same population. And so the task of identifying from spectra chemically identical stars is equivalent to that of identifying open cluster siblings. Now, from a practical perspective, what this means is if we can train a data-driven model that goes from spectra and is able to identify stellar siblings, then we can also use that model to identify chemically similar stars without ever needing to use synthetic spectra. So this rests on a key assumption, which is that open clusters can only be identified from spectra by their chemistry. Now, there's a few ways in which we know that this cannot be the case, and that's because open clusters share the same common spatial location. So on top of sharing a common chemistry, they also share a common velocity, distance, and extinction. And if we don't mask these features, then identifying open cluster siblings isn't just going to identify chemically similar stars, but also chemically similar stars with common velocities and distances and extinctions. So we need to remove these features. And the way we do this is to remove a velocity, we shift to the rest frame. To remove a distance, we pseudo-continuum normalize the spectrum. And to move into stellar features, we mask the location of diffuse interstellar bands. So now how do we actually go around building such a model that can recognize stellar siblings? Well, one approach is using machine learning and using something known as metric learning. And so here on the left, I've shown a scatter plot, which is supposed to represent like a data set of like stars, like a toy representation. And every color is an open cluster, and every scatter point is a star. And you can imagine the dimensions to be pixel intensities or maybe stellar parameters. Well, then what metric learning tries to do is it tries to transform this representation in a way where the distances between stellar siblings are minimized. And so you can find stellar siblings without knowing the colors, without knowing which stars are part of open clusters, then by just looking at how close stars are in the space. So this is known as metric learning. But how do you build such a model? How do you build a metric learning model? Well, we show one approach in our paper, which is like a novel approach. And the idea in our approach is first we compress spectra down to a lower dimensional representation. And we do this using PCA. And this serves to work in a lower dimensional space because we don't have very many open clusters. So we want to make efficient use of the data. Once we're in this lower dimensional space, we apply a set of linear transformations, which essentially what they do is they decorrelate the dimensions. So this is steps 2 and 3. And once we have the dimensions which are decorrelated, what we can do is we can rescale dimensions independently, look at each dimension independently, and rescale them based on how useful they are for recognizing open clusters. And the way we do this is we compare the standard deviation, the scatter, along dimensions for the full population of stars, field stars, and for cluster stars, stellar siblings. This gives us a measure of how useful that dimension is for recognizing open clusters, and so how much chemical information it contains. So this is entirely linear, so the whole algorithm is linear. So now we've got an algorithm. How can we actually evaluate it and measure how well it's doing? One approach is to measure doppelganger rates, which is this idea coined in an old paper of Melissa Ness. And the idea is essentially that doppelganger rate is the percentage of field stars that are as chemically similar as stellar siblings. So this gives us an idea of how discriminative a representation is of stellar siblings. And the way we calculate this is we look at the distribution of pairs of stellar siblings, and then we look at the median value of this distribution, and we look at how many pairs with field stars have a value lower than this median, which is this red area. This gives us an idea of how discriminative our representation is. Ideally, we'd want the doppelganger rate to be 0. So we can apply this to APOGEE data release 16 and the OCAM value-added catalog. And so we have a data set of 185 open cluster stars distributed across 22 clusters. And we can look at the doppelganger rate that we'd get from spectra and compare it to the one we'd get from abundances. And we can also look at the doppelganger rate we'd get without this metric learning step and just measuring the distances in the raw space. So in the raw space of spectra, distances are not very discriminative of stellar siblings. And the reason why is because there's non-chemical parameter factors of variation. But once you apply this metric learning approach, you're capable of removing all of these non-chemical factors of variation like temperature and systematics to get a much lower doppelganger rate, which is lower than the doppelganger rate from abundances, which when you apply directly, when you measure directly distances in abundances, you get the low doppelganger rate already because you've already removed all the non-chemical information. But it doesn't improve very much because you've thrown away some information in the transformation from spectra to abundances. So now another thing we can do, which is another way of looking into these results, is we can look at essentially how these features that the model recovers correlate with known galactic features. So a model is essentially just scaling dimensions in a data-driven model of spectra. We can look at these dimensions, like the most strongly scaled dimensions, and see what they correlate with. So if we plot the most strongly scaled dimensions of a dimension our model picks up as the most useful for identifying stellar siblings, it pretty much correlates with the metallicity. It's almost a one-to-one mapping with a little bit of scatter, which is expected because this is a linear feature of spectra, while metallicity is a nonlinear parameter. If we look at the second feature, then it looks very much like alpha elements, and we recover the alpha element by modality. And what's interesting is we're able to recover metallicity and alpha elements in a purely data-driven way without giving any information about these things. Neither the abundances nor the synthetic spectra. What's interesting is also we're able to recover this alpha element by modality, even though all of our training samples, so all of our open cluster stars, are in the lower half, which shows that the model is able to generalize quite well because it's linear.
Damien,
we can also see the third feature, which I've shown here, like just for completeness. There's more features after this one, but just to be more complete. And what this is showing us essentially is that I think this is a non-linear feature of metallicity. And this is just a higher order term of metallicity because metallicity is nonlinear, so you need multiple linear terms to fit it. So that's the big of my results, my main results. And I'm just going to leave this conclusion slide while I let the floor be open for questions.
Great, thank you so much, Damien. Questions? Just give it a second here. I'll ask a question while we're waiting. I guess not knowing much about this metric learning and approaches like it, how do you, how do you sort of determine what these different, your features 1, 2, and 3 are correlating with? Do you just plot them with the known parameters and see what looks like it correlates? Or
this is this plot. So essentially, our method essentially finds a basis, which I'll show here. Where is it? Here. So essentially, find the basis, and this basis we scale vectors, So what we can do is we can look at which vectors are scaled most strongly without necessarily giving any chemical information or any prior information. In the direction which is most strongly scaled, you can plot it against metallicity, and you see that there's almost a one-to-one mapping between these, which is showing that it captures metallicity. If you look at the second most strongly scaled dimension, then it's really matching with alpha elements. So in some ways, this is just picking up on the fact that metallicity and alpha elements are like kind of the most important features in spectra for recognizing stellar siblings, and all the other features aren't nearly as important.
And do you expect that they, I mean, could some of them be a combination of multiple elements, or?
These features?
Yeah.
So we're independent. So like essentially we're working in a basis where like the features are decorrelated. So all the features are independent. So if so there's only one feature associated to every factor of variation. And like this kind of like decorrelating of dimensions is very effective for isolating away the different factors of variation, it seems, because we're able to get metallicity in one clean dimension and alpha elements in another clean dimension. And so far that like we're recovering all of the features without any contamination that we would expect in each feature.
Okay. Questions from the audience? Yeah, Michael, do you want to ask your question? I can read it out if it's too much trouble.
Yeah, so this is maybe putting Thomas Nordlander on the spot, but my question is more about how important is the assumption that the open clusters have uniform abundances in your analysis? So we know that in young open clusters in particular, you see variations in abundances due to chromospheric activity. And so you might not actually expect the abundances to be uniform depending on how active different stars are in the cluster.
Yeah, so I'd say that's not, that assumption isn't that big of an issue, because essentially the model is just using any information that can be useful to recognize stellar siblings. And even if it's not uniform, it's still going to pick up on features if it's discriminative. I'd say the kind of like the more key assumption is that like abundances are the only thing in the spectra which you can use to recognize stellar siblings. But the fact that abundances are uniform, what it allows is it means that the representation that it's going to find is going to be like optimal in the sense of a noise, where it's going to pick up on features proportionally to how discriminative they are of abundances. So it's essentially going to like scale features proportionally to like your confidence in like your error bars on those features. And if uniformity isn't true, then like that won't necessarily be the case.
Okay, thank you.
Great. So Thomas says that hopefully the chromospheric activity just looks like a stellar parameter.
So this approach essentially like any difference, like the kind of a motivation is for this kind of approach is that anything that's like not helpful for identifying open clusters within the spectra is basically discarded. So this is a way to remove all of your non-chemical factors of variation essentially. And you can apply it to any spectra, even like for stars which you don't have very good chemical models, to get kind of an idea of a chemistry.